Thank you very much, Mary Beth. I should just say that in the years that Mary Beth and I were on the Polar Shelf Committee, she sat opposite me. So I was here and she was there, and as I started talking or introducing somebody's review, I'd get this look. And if the eyes went down, I knew, like the eyelids were going closer like this, I knew I had to be careful. But otherwise, the eyes were just like this. And then you think, oh, that's good, I'm fine. I'm fine, we're not going to have trouble. But thank you very much all for coming, and thank you very much, Mary Beth, for the invitation. I'd also like to thank Melanie for all the arrangements that you've made, and that's really been very nice for you to do this. I'm going to talk to you about permafrost after equilibrium, but I'm also going to talk to you a lot about the work of Ross Mackay. And the reason I'm going to do that is that in 1964 and 1965, he was the chair of the Board of Governors of the Arctic Institute of North America. So he has a long-standing association with the Institute, although in those days the Institute was in Montreal, it wasn't actually here. Now, at the time that Ross was the chair of the board, that is the 1960s, he took periglacial geomorphology and he converted it from a discipline that was largely consumed by historical questions to the process-based inquiry that we know today. This enduring development began in 1959 with his analysis of the ice thrusting of Herschel Island, which he published with Bill Matthews. And then it became established in 1962 when he wrote his first Pingo paper, and then the big monograph from 1963 on the Mackenzie Delta, which we still cite again and again today. The only person at the time who was working in the same way, which is kind of the engineering approach to earth science, was Peter Williams, and he died last year. Ross died in 2014, and part of the reason that I'm going to draw your attention to Ross Mackay is that quite a lot of people think that anything that was published before the internet wasn't published. And there's lots and lots of people studying permafrost these days. Many of them don't live in North America. Many of them have never taken actually a course on permafrost. And so it's quite difficult for them to look at the material that is the foundation and is the benchmark against which we measure what is happening today. And we're extremely fortunate in Canada to have Ross Mackay's legacy, because from the 1960s and 70s, we know what things were like before climate change. There's relatively few disciplines in which we actually know that, particularly in terms of Arctic studies. So I want to talk to you a little bit about equilibrium, because the equilibrium approach has two main characteristics. The first is that physical principles can be used to investigate steady state configuration of systems. And the second is that departures from steady state can be assessed probabilistically. It's an approach that Ross used very successfully, for instance, on his papers on the equilibrium model of hummock formation. And it's also one that he used consistently when he was trying to assess how often things happen. He probabilistically classified ice-wedge activity from a 20-year record of cracking of 30 ice wedges from Garry Island, which he used to calibrate his system. The principles of landscape behavior that he used when he was looking at how frequently these things occur were ahistorical. In other words, the 20 years that he used to measure what was happening and when it was happening could have been any 20 years. They were 1967 to 1986. That was actually the 20-year period. But from the analysis that he used, it didn't matter that it was then and it wasn't 20 years before or 20 years afterwards. Now, Ross fully appreciated that the landscape is actually a product of history. And he revealed this in his recognition of what we call anti-syngenetic ice wedges, those that are formed on eroding hill slopes. Nevertheless, when we look at his work and when we look at the thinking which pervades most earth science or surface earth science, we do not get a sense that the landscape is making history. Robert Macfarlane, who some of you may have heard of or maybe even have had the experience to have met, points out in his book, The Old Ways, that the word landscape entered English in 1598 from the Dutch landschap, which at the time meant scenery as depicted in a painting. It's only from 1725 onwards that the word was used to mean the physical structure of the land which we can see ourselves, and even then, the landscape was not, and still in many cases is not, seen as dynamic. Some might have gone so far as to suggest that the landscape is immobile, but a dynamic equilibrium is more commonly understood, that is, a steady state. So this culturally conditioned view of the landscape may be at the root of the excitement expressed by observers of retrogressive thaw slumps or of Thaw Lake drainage, for they see the landscape change before their eyes in ways that are, in some instances, irreversible. It also accounts for publications that report observed changes at places revisited after only a few years of thaw degradation. Visible deformation of the landscape is not what we expect. We may anticipate events in steep or alluvial terrain, but we do not anticipate widespread adjustments to scenery. There has been a steady climatic warming in the Western Arctic for nearly 50 years, such that at Inuvik, the mean annual air temperature has risen by over 3.5 degrees Celsius from its average in the 1960s of minus 9.7 Celsius to minus 6.0 in the last decade. The annual mean air temperatures are well correlated throughout the Yukon and Mackenzie Valley, so what you see on the slide, the trend there, is a regional phenomenon. There's no suggestion in any projection of future climate that this change will be reversed in the next century, and there are many projections which indicate the warming will accelerate. Most of the change that has been observed since 1970 has occurred in the winter. The annual mean temperature in 1998 was at the time the warmest year on record, and it was then interpreted by Geological Survey of Canada scientists as a 1 in 300 year event. But now it would be considered much less unlikely, and indeed that was the value that was measured in 2019. Back in 2003, I had an opportunity to examine the climate change that was then projected. And this took place at a meeting downtown in Calgary. And what we did then was to gather some people together in the context of the Mackenzie Gas Project and try and produce projections for the climate change that was anticipated over the life of that proposed project. The idea was that we would then not have an argument in the public hearings about whether climate change was or wasn't occurring. We would know what it was that we were trying to manage over the life of the project. And on this slide, you will see the projections that were presented then with the actual trajectory that has been experienced. And these data are 30-year averages. They're not 1 year here or there. And you can see that in the Western Arctic, the projections have been exceeded. An increase in rainfall has also become apparent in the Western Arctic in the last 20 years, but the adjustment is not as well correlated across the region. At Inuvik, the rainfall record extends from 1958 and includes 3 years with incomplete data, which gives us about 58, 59 years in the record. These data are presented here on an exceedance probability plot. So that means that they're ranked from largest to smallest. In a uniform distribution, we would expect 1/3 of the highest third of the rainfall totals to have occurred in the last 19 years. In fact, since 2000, over half of the highest 20 rainfall totals have been recorded. The increase in rainfall is greater than the relatively high projections of future rainfall that we made in the early 2000s for an ensemble of GCMs. So what these do is to tell us that both temperature and rainfall series show that the climate is changing in the Western Arctic, and the adjustments are entirely consistent with what we know about an enhanced greenhouse effect. The only difference is there's more of it than we anticipated 20 years ago. Now, the role of a scientist is to provoke new questions that lead to deeper understanding of environmental systems. But science is largely sponsored because it also delivers technique. That is, the ability to control or to manage nature. Up to now, our science of the permafrost environment has been either equilibrium-based or historical. In fact, we have standard terminology for the past, including for time before the present. BP, we write. But we do not have standard terminology for the future. There is no AP after present. Furthermore, when we have looked to the future, we've characteristically worn equilibrium eyeglasses, or at the most, gradualistic spectacles. The gradualism we inherited from Charles Lyell. But as Barbara Kennedy repeatedly pointed out, both equilibrium thinking and gradualism have a limited role in developing understanding of Earth systems. Victor Baker, of course, reintroduced the idea of catastrophism to our mental maps of both the past and the future. But in that case, he focused on very specific events. I would like to suggest in the remainder of the time I have with you 3 ways of looking into the future of the permafrost environment. First, gradual adjustments to the ground conditions that have issued from climate change over the last 50 years and how they can be expected to proceed. Second, large magnitude events that are new in the record. And third, acceleration of processes that were previously considered to be gradual. I know that precision in forecasting events in the future is poor because the precise trajectory of climate change is yet to be revealed, because it depends on emissions pathways. So that means that the future appears to us not as a single mirage, but as a series of alternatives. And in each case, as I go through these 3, I will refer to the work of Ross Mackay as the baseline. But before I do that, I would like to orient you to the field area. The map on this slide was prepared by one of my friends, Brendan O'Neill, who works at the Geological Survey of Canada. And I'm going to discuss data from 3 locations in the Western Arctic. And if this is the pointer. So one is Illisarvik. And Illisarvik is the lake bed, or that was drained by Ross Mackay in 1978, when he decided to initiate Canada's longest running field experiment in the permafrost environment. He drained the lake in order to initiate permafrost growth into the lake bed and to study what was going to happen as permafrost grew. The second location is Garry Island, and Garry Island is a small island in the outer Mackenzie Delta where in 1964 Ross built a cabin so that people could go and stay there year-round. His cabin is only half the size of what he intended, so it is a cabin. Some people refer to it as a shack, but I think that is very rude. It's a cabin, but it's half the size because there was another person at the time called Don Gill that some of you may have heard of. He is a legend in some ways because his consumption of alcohol and at the time restricted substances was legendary. Anyway, Don Gill also needed a cabin, and so Ross split his cabin in 2, and half of it was put in the Mackenzie Delta at a place which is called Gill's Camp, surprisingly, and the other half of the cabin was on Garry Island. The Gill's Camp, in fact, was placed on land which is now part of the Inuvik settlement region, private land, so it's been taken away and was turned into a place where someone kept chickens over the winter. whereas Garry Island cabin is fine, and there will be a picture of it in a few minutes. The other area I'm going to draw your attention to is the Caribou Hills, which is on the edge of the Mackenzie River. And they're about 40 kilometers downstream from Inuvik. So some of you may be familiar with these two maps, which we published in 2009. In these maps, we compared measurements of ground temperature in the Mackenzie Delta. So the first on the left, you'll see measurements of ground temperature that were compiled by Ross Mackay between about 1968 and 1972 from industry boreholes that were drilled in the oil and gas exploration that was taking place at the time. This is a compilation of something like 200 boreholes, data from 200 places. If you look at that map and then compare it with the map on the right-hand side, which is a compilation from data that was collected by people working in the Mackenzie Delta area in the first 5 years of the 2000s, that is of this millennium, then you'll notice that almost ubiquitously across the region, ground temperatures had increased by about 2 degrees Celsius. So even though we had had only about 35 years of warming from that curvature in 1970, the permafrost environment was adjusting. 2 years ago, that is in 2017, we showed that these data that are on this slide represent a minimum regional increase in permafrost temperatures because the values are higher at sites that were disturbed, such as in drained lake beds. However, what I want to point out is that Ross's data produces a baseline against which we can assess future environmental change. So now we're going to turn to the gradual warming. We won't discuss this for long, partly because it is an area in which there has been considerable publication, but also because I want to return to it at the end of this talk. I'm going to introduce one of the issues that has focused minds in the Western Arctic in terms of the implications of climate change in the permafrost environment. But I do want to point out that Illisarvik has offered an opportunity for long-term investigation of both the lake basin and of conditions in the surrounding undisturbed tundra. What I'm going to do on the next slide is to concentrate on ground temperatures that have been measured in the tundra at some boreholes drilled in 2003 and 2006, and which we have monitored closely after that. Section C of this slide shows ground warming in the tundra has occurred throughout the monitored upper 50 meters of the ground. The data show that ground temperatures decrease with depth rather than increasing with depth, which is the equilibrium case. So that's this slide here. You'll notice that the increase in temperature is greatest near the surface and declines with depth. That observation that we see here at 10 meters is replicated at a second temperature cable on Garry Island, and these observations are replicated on a second temperature cable at Illisarvik. The rate of warming is highest near the surface. If we look at panel A, which is at the very close to the surface, right at the top of permafrost, you'll see that at present rates of change, we may expect the temperature in sandy material at Illisarvik to approach -2 degrees in the uppermost 5 meters by 2030. When the continuous permafrost throughout the Western Arctic at that temperature at -2 will be considered sensitive for engineering purposes. The sands at Illisarvik are a product of the glacial history of the area, both from outwash and aeolian processes. They create the conditions where temperature change in permafrost can be relatively rapid, as latent heat effects are minimal until the ground is close to 0 Celsius. This leads us to consider a direct consequence of the non-equilibrium environment. Drilling waste sumps, sealed in permafrost in the 1960s and 70s in the region, may then no longer be effective containment structures. When these were built, or when these were designed, the idea was that permafrost would be frozen forever. the temperature was -8. And when they dug out or blasted their hole in the permafrost and threw drilling waste and other stuff, peanut butter, diapers, trucks, all kinds of things into the ground, then the idea was they would be contained within the surrounding and enclosing permafrost at -8 Celsius. But as we approach temperatures, say, -2 or -1, then permafrost is likely to be no longer a containment. The key question is, when will that happen? Will it be in the next 10 years? Will it be in the next 20 years? Will it be in the next 30 years? If we know the timescale, we're in a position to manage it. There are about 170 sumps in the region. So each of these sumps, if it is to be mitigated, will cost $1 million at least, because all of this material has to be dug out of it and then brought from the Western Arctic to the province of Alberta. So you guys will ultimately receive all of this unless the sumps fail and the materials go into the ocean or go into an adjacent water body. The issue with these sumps is that they were built by industry, but they were permitted by the federal government. So the Inuvialuit know that it wasn't them that built the sumps, but they're the landowners in many cases, or it's associated with their traditional territory. So everybody in the room is probably going to be on the hook for some of the cleanup costs of these items. At the moment, we've got time to determine how to manage these contaminated sites. But given the scale of the problem, we probably don't have too much time. The rate of near-surface warming will reduce as the temperature gradient steepens and more heat is conducted into the ground. But even if climate warming ceases, a model that has been calibrated over the last 7 years indicates that the tundra permafrost at Illisarvik will reach about -2 in the next 20 to 30 years, 20 to 50 years. So this is a model that has been developed by Yu Zhang, who works at Natural Resources Canada in Ottawa. And what he's done here is to calibrate the ground thermal regime in the Illisarvik area against measurements of temperature that we've provided to him. And then he's used that to project forward given present climate, not given a change in climate, but given present climate. And you can see here how near the surface of the ground temperature reaches -2, which may not be able to contain the waste relatively quickly. Climate change also presents new events in permafrost, such as we have not witnessed in these landscapes. But for us to notice new events, they normally need to be sudden and big. So I will draw your attention to landslides, especially an event that took place 2 years ago. These events are the product of changing precipitation, which in turn is related to the change in temperature, but it's the precipitation which is the immediate impact. The Caribou Hills are about 30 kilometers down the east branch of Mackenzie River from Inuvik. They were briefly described by Franklin in 1825, and Richardson's journal, published in 1851, includes an etching of the area in these photographs. In 1954, John Stager took the picture on the left, and in 1963, Ross Mackay took this picture. And you will notice in the 1963 picture, there is a fan at the base of one of these gullies that has come down from the Caribou Hills. So we know that in the past, there have been landslides in this area, but occasionally. In 2009, a series of landslides occurred on the hills following very wet conditions towards the end of September. My friend Douglas Esagok, who lives in Inuvik, had been on the water at the site just before that storm at the end of September and came back to Inuvik. He couldn't go out on the 19th, 20th of September because it was raining so hard, but on the 21st he went back hunting down the Mackenzie Valley and he saw 11 of these landslides, this being the most spectacular of them, at the edge of from his boat. So we know the date when these things happened. If you look at an aerial photograph or a satellite image from 2004, you can see that there are relatively few landslides in this section of the hills adjacent to the Mackenzie River. But in 2010, you can see several of the ones that were triggered by that rainstorm at the end of September 2009. There were 25 landslides triggered by that event in 2009. If we look at the next slide, you'll see again, I've placed Ross's picture or John Stager's picture from 1954 here, and you can see these hills here which were unaffected by that 2009 event on this side here. And this picture, as you can see, is taken in 2011. Now, on the night of the 25th of September 2017, there was a heavy rainstorm in this area. There was a camp at Reindeer Station, and the people who were living in the camp were scared for their lives because a series of landslides came down the Caribou Hills, and these landslides, fortunately, did not wipe out the Reindeer Station camp itself, but adjacent to the camp, there were a series of these incidents. In one night, there were in 11-kilometer section of the Caribou Hills, there were 87 incidents that took 87 landslides. And there were 2 or 3 cabins that were almost taken away in this region. So this is an example of a large-scale event that is, in a sense, unprecedented in the record that we have. If we go back to the 1954 area, there's the picture from Ross, and here in this area is 2 of them that have come down just at the same location. Something that's much larger than anything that has been in the record. Adjacent to these landslides is that one that I showed you from previously, from 2009. And you'll notice that this one here didn't have very much activity at the bottom. And this is associated with a phenomenon that we refer to as event resistance, which is a name that was given to it by Mike Crozier from New Zealand. And that is that in the time since 2009, there was insufficient period for the weathering of the materials at the top to create a sediment reservoir which could then be removed during that large event in 2017. In other words, individual events in individual places may not occur again immediately in the next event, but statistically they're likely to occur at some time in the future. But once something has happened, for example, in this area here, we wouldn't expect something to happen exactly here again in the next maybe 10 years or so. I'd like now to draw your attention to effects which are occurring gradually, but which become accelerated as a result of climate change in the permafrost environment. And in particular, I'd like you to think about subsidence of the ground surface. Now, Ross Mackay produced a paper that was published in 1990 in which he introduced to us the idea that ice wedges, which are the bodies of ice that outline tundra polygons, are also found on hill slopes. It was the case up until then that we anticipated we would find them in flat, low-lying ground. And so the tundra polygons that people think about for large portions of the Arctic environment are characteristically best observed in lowlands, not in areas where there is erosion and hill slope movement that may obscure the outlines of those polygons. Here is an area, again, close to Illisarvik. Illisarvik is the drained lake basin on that side of the photograph. But here we have a line that comes from one lake here up and over the top, where Ross Mackay installed in 1983 a series of sites at which he could measure the depth of thaw into the ground. Now, I'm going to be showing you data from this Hillslope transect where there are 12 locations where since 1983 we've measured the depth of thaw every year. But I'm also going to show you some data from this little ditch that you can see on the hillside over here. And at this location, we're measuring how much the ground is subsiding as a result of increases in thaw progression. So this is data that were produced over the period 1983 through to 2018. The open circles were published in 2009. These black ones are not published yet. But you'll notice that over that period of time, on the average of 12 sites on this hill slope, we've had a consistent increase in the depth of summer thaw above permafrost. This is quite widely known and reported in a large number of places. So increasing active layer thickness or increasing thickness of the ground above permafrost that thaws out every summer is something that is relatively well known. However, most of the data that we have from around the world starts around about between 1990 and 1995. So the conditions that were occurring before then, which we again thought of in those times as equilibrium conditions, are characteristically not very well known. So now I'm going to move you over to that ditch on the hillside, and this is a picture that Ross took in 1993. And you'll notice that there are two field assistants here, and this guy, whose name is Chris Diana, he probably comes up to about here on me. He's not very big. This fellow is much taller. He's about my height. I don't want you to think of the height of their caps as indicating where is the ground, but if you think of roughly where their feet are, you will see there's their feet and there's the depth of the depression. The next picture is taken of this at almost exactly the same place, but with different people in 2013. Now, these people are all taller than the people on the previous slide. But even though they're taller than the people on the previous slide, I think you will note that the trough here has got deeper over that period. That this person's feet are lower than this one, and these two on either side are around about the same. The next slide is going to be almost at exactly the same place, where we have a series of benchmarks, these orange stripes on the picture, and these benchmarks were installed in 1996. And they allow us not only to measure at the same place the depth of thaw every year, but they also allow us to measure how much the ground is subsiding every year. And you'll notice in this case we have the top of the benchmark, which we can measure with a level, an optical level, and we can measure that to better than a millimeter. And then we can measure the distance from the top of the benchmark to the ground surface. And everything that I'll be showing you is with respect to the adjacent ground surfaces. So there are 3 of these benchmarks in the middle of the trough. There's one on either side. And then in the next picture, we shall see the one that's over here and one on this side. Now, I'd like you to notice this, of course, is taken in the summertime, and the next picture is taken in the wintertime. So here we have the same trough with the 2 benchmarks on either side of the trough, but the trough is so deep now that it's covered in and you can't see the benchmarks, even though they stick up about 80 centimeters. You can't see them in the trough, they're covered over with snow. There is a benchmark on the other side of the polygon here, and then another one on this side. As this trough gets deeper and deeper, and it collects more and more snow, it gets warmer and warmer. And because it gets warmer and warmer, it gets deeper and deeper. And therefore, the development of the troughs is a process that has considerable positive feedback. In other words, it's self-perpetuating. Now, this slide here gives you an indication of the thaw depth in the polygon, that is the sides on either side, and in the middle of the trough, and also gives you an indication of the subsidence that has been occurring. So here we have the ice wedge. That's the middle of the trough. You'll notice that the thaw depth oscillated around. It was quite high in 1998 or so, and then it's come down. But since about 2006, the active layer in the ditch, that is above the ice wedge, the active layer has actually not changed at all. In the adjacent polygon, the active layer has been increasing, just as it was on the hillslope transect that I showed you with those 12 sites. So the polygon shows us what's basically happening in the region, but the ice wedge is a little different. However, if we look at the subsidence, and this is relating what the ground surface levels are on either side of the polygon, you'll see the polygonal subsidence, that's the open circles, basically there's not really very much subsidence. Over 10 years, there's been about 10 centimeters. But look here at what's happening above the ice wedge. Since about 2006, the ice wedge has been going down and down and down. It's gone down something like 45 centimeters from where it was when we started measurements in 1996. And that adjustment has a hinge point at 2006. So if we look at what's happening here, you'll notice that we have an ice wedge under the trough, and above the ice wedge there is some soil. That soil is now the thickness of the active layer. So that every year, as the active layer reaches the top of the ice in the ice wedge, it melts the ice. And because it's on a slope, the water is just dismissed downslope. So the water is thawed and then it's evacuated. And as a result, there is significant amount of subsidence on the hill slope above the ice wedge. So this is an example of how pre-existing conditions, that is, pre-existing ice wedges, influence the response of the terrain to climate change. Now, Richards Island, Illisarvik is here on Richards Island, and if we look at Richards Island, the orange areas are areas where the ground slope is greater than about 2.5 degrees. Therefore, they're the places where the water can move away when it's thawed. So this indicates that something like half the island is susceptible to this kind of material, or this kind of activity. So this indicates that there's a significant amount of the terrain in the region in which accelerated consequences from climate change are to be expected. The strangest consequence that I've observed is the development of a lake on a hill slope. Most of the lakes that we see are in lowlands or at the bottom of valleys or something. But in this case, we have an ice wedge that runs with the contour. In other words, it's perpendicular to the slope. So it's running along the contour. And as the ice wedge deteriorates, so it was excavated by Dr. Mackay in 1993. This is the same picture. That alder bush there is that alder bush there. So as it was excavated and disturbed. And when it was disturbed, thawing began. And as thawing began, the ice wedge that's underneath began to melt. But the ice wedge went down, but the ground on the other side didn't go down as much. So we had the development of a trough that ran along the contour. And the water was contained in the trough. Any water that was coming downslope through runoff was contained in the trough. So now we have the beginning of a thermokarst lake on a hill slope where the slope angle is about 3 degrees. I'm going to finish the scientific element of this presentation by taking you back to a site that Ross Mackay examined in between 1969 and 1971. He published the results of this in a journal that is called Arctic, and it was published in 1974 by J.R. Mackay and D.K. Mackay. And there is the chalet or cabin on Garry Island, and I've painted it, so it looks different from when Ross painted it, but it's painted it more recently. Across the little valley that the cabin is located in, he identified a series of sites that you can see here by these dowels that I've erected. We were able to reoccupy exactly the same places as he studied from 1969 to 1971. During that time, he ran cables from each of these sites into the cabin, and he attached the thermistors in these sites in the cabin to a chart recorder. The chart recorders were run by car batteries. And every day over the year while he was away, the chart recorder made a little piece of paper and a little graph as to what was the temperature at the bottom of the active layer. And then he took these charts home, that is to Vancouver, and he spent time with a microscope or with a magnifying glass determining what the temperature was on every single day of the year. Now, don't forget, in those days, they didn't really have very efficient, Excel or anything like this. So he'd have to write that down, and then he'd have to put it in a machine, which I don't think he turned like this. But I think they did have an electronic calculator by 1971, and he calculated the mean annual temperature at these 10 locations. Now, the key point about this is that across this hill slope, the conditions vary, so that the bottom here is very wet because it receives all the runoff from the adjacent hill slopes. But in addition, at the bottom of the hill slope on this side particularly, and also on this side, at the end of the winter, there's usually a very big snowbank, whereas the top of the hill slopes have the snow blown away from them. This transect is in the same direction as the prevailing winds, which either come from the northwest in the winter, the storm winds, or they come from the southeast on this side. So what he's able to do was to look at the influence of snow conditions on near surface ground temperatures. This was really the work, the first work, that we nailed down the influence of snow on near surface permafrost temperatures. Now this takes place, this study that we're doing now takes place in an environment where we know that the ground is warming up. And the question that we have is whether the ground is warming up fastest under the places which are already warm because they're under a deep snow cover, or whether the ground is warming up fastest at the tops of the hill slopes where there's little snow cover, but most of the climate change takes place in the winter. So they're therefore more responsive to winter conditions, or whether it's happening somewhere else for some other reason. So what we've been able to do over this period is not with running cables into the cabin and having car batteries, but having miniature data loggers at each location, we can determine what the temperature is at each of these locations. So what I've presented for you here is, is the data from 1969 to 71. This is the data that Ross published in Arctic. And you'll notice that on the hilltop we have relatively cold temperatures, similarly in the valley floor, both places where there wasn't much snow, and he interpreted them in terms of snow. And then at the base of the hill slope where there's a big snowbank, relatively warm conditions, and then kind of moderately on the slope. Now if we go 35 years to a next period, and I'm giving you now the average of 4 years data from 2006 to 2009, so that's 6, 7, 8, and 9, which is 4, then you'll notice that in each case there's been an increase in temperature. And then if we take 10 years past there and go to the most recent 4 years, you'll see there's been further increases in temperature. You'll notice that the warmest is still under the slope, but the greatest change in temperature, the warmest is still at the bottom of the slope, so that's minus 4.2 degrees. And I should say this is the average of 4 years, so there are years in which the temperature is greater than minus 3. So we're already, in some of these locations, reaching that value which is a problem for the sumps. So this is still the warmest place, but where it warms up the quickest is actually in the valley floor, where there's relatively little snow. But you may remember I told you that the valley floor is very wet. So what's happening here is that the amount of time it takes for the ground to freeze up is being elongated. So it's taking longer and longer to freeze the ground, and therefore the ground doesn't get very cold in the winter because it doesn't have as much time to get so cold. So even though we would think of this initially in Ross's terms as snow cover, when we see something new happening in the landscape, there are other things that become important. It's not just a univariate system, but it's a multivariate system. And so the main message from here is the extent of total warming would not be available if we didn't have what we have from the 1970s. But even so, the actual event is something that we need to change our interpretation. But then the question has changed, because the question is not what is the case, but the question is what is going to be the case. So I'm going to conclude by asking you to think in summary about the permafrost environment and the engineering challenges that it poses to us. In 1944, T.S. Eliot pointed out to us in a speech that he was giving to the Virgil Society, which is a European literary society. It was published in 1945, so this is during the war. And he says this: "In our age, when men seem more than ever prone to confuse wisdom with knowledge and knowledge with information, and try to solve problems of life in terms of engineering, There is coming into existence a new kind of provincialism, which perhaps deserves a new name. It is a provincialism not of space, but of time, one for which history is merely the chronicle of human devices which have served their turn and been scrapped, one for which the world is the property solely of the living, a property in which the dead hold no shares. Eliot was describing the consequences of modernism. Henry Ford's history is bunk. But we live in postmodern times, when, for example, the Yellowknives Dene do not want remediation and erasure of the giant mine's environmental legacy, because they want us all to remember what happened near Yellowknife. An equilibrium approach to permafrost is ahistorical, but the history of the Western Arctic, particularly in terms of the occurrence and preservation through the Holocene of ground ice, is coming home to roost now that we have changed our climate. Our infrastructure system is based upon engineering solving all our problems, given adequate resources. Some of the infrastructure challenges we are encountering in the permafrost landscapes will not be addressed by conventional engineering, because the population size cannot justify the capital outlay required from the public purse. But this will not stop climate change. Some years ago, at an ACONS meeting, Bob McGee gave a survey of archaeology of the last 50 years in the Arctic. And one of the things he identified was that we've changed our narrative about what are the causes of change in society. At the moment, we all know that colonialism has a very bad rap. I asked him at that meeting, in 50 years' time, what will people look back and say, those people were really ignorant, they were really bad? And what would we, if we were here in 50 years' time, what would we throw stones at when the 50 years' time people are looking at us? I actually expect it will be about our response to climate change. We are going to find out that we do hold shares in the future, and I think that we might be despised. So I'd like to finish just by thanking the late Dr. Ross Mackay for giving us all of that baseline against which we can think about how the future may roll out in the Western Arctic. I'd also like to acknowledge particularly Douglas Esagok, who is from Inuvik and who I've been privileged to work with since 1997. But there are many other people who've contributed to this. But I think that what I hope I've done is to give you some way about thinking about climate change with examples, rather than actually telling you what is going to happen. Thank you.
So we have time for questions, if there are questions from the audience.
Brian.
Thank you, Chris. That was most enlightening. And I like the way you structured it with the, constant, gradual, or sudden change idea. And it's got me thinking about, are there sudden changes that we've not experienced at all? We don't even know they're going to happen. Surprises around the corner. There seem to be all kinds of surprises these days. But particularly about the trough going down the hillside that's ever deepening, and I think you're alluding to the point that the ice is melting out of it, causing the deepening, but could there be also that it's washing sediment out as well? Were you able to determine whether that was part of the deepening as well?
There are cases at the bottom of hillslopes where we see what some people refer to as gushers. And this is where there is a spring that emanates, and it actually it's turbid water. It's not clean water. In this particular case, every year there might be 2 or 3 centimeters of ice that is melted. That ice has a density actually less than 0.9 because it's got a lot of bubbles in it. And that is seeping out really over a period of about 6 weeks, from something like the middle of August to something like the end of September. So the quantity of water that's going down the slope is not great, and it doesn't travel at a speed that enables its material to be removed. The other point is that you're probably familiar that at the bottom of the active layer, in much of the Western Arctic, there's an organic horizon. And that organic horizon is the topic that I don't work on, which is carbon in permafrost. But the organic horizons are relatively cohesive because the fibers in those organic horizons mean that individual particles are very difficult to detach. And therefore, the water can go through the organic horizon just like water goes through a sponge in your bathroom. And it doesn't carry with it the stuff that was on top of the sponge. So you don't get soap coming out through the sponge. You get the frothy soap still stays on top of the sponge, whereas the water comes out the bottom. So it's that same environment. And that's because of this organic horizon. And that organic horizon, maybe on top of the ice wedges, it might be 5 centimeters thick, but in the surrounding ground, it might be 30 centimeters to a meter thick.
So now you mentioned sediment. I was wondering about the sediment load that's coming off those slumps. It's all going into the Mackenzie and then out into the ocean.
Mm-hmm.
So, I mean, it's not just a landscape change issue. It has to be a affecting the biogeochem
Mm-hmm.
of both the river as well as the ocean. So, who's tracking that?
So there's the cases where this effect is the greatest is in the creeks or small rivers, right, which drain some of the lakes, where the thaw slumps are actually on the edges of the creeks. If you let me digress a little bit, one of the interesting things here is that between about 8,000 years ago, the climate of that part of the Western Arctic was warmer than what it is at the moment. And yet we see very few thaw slump scars that are relict from 8,000 years ago, but they're so big today that they would never have been filled in with sediment. So the landscape would not have healed itself over that time. We would still have seen that, but we don't see the relic. The reason for that, I think, is that over 8,000 years, the creeks have incised and created valleys, and the incision of the creeks has created slopes in which these landslides or thaw slumps can take place. And then, particularly the increase in rainfall has led to that. The people who are looking at that quality is actually the fisheries biologists, because the most important impact of having a large amount of sediment in the rivers is on whether they destroy the habitat for various fishes. So those are the key people. There are a number of Germans, actually, who are working in the area, who are interested in the transport of carbon into the ocean. But I wouldn't refer to them as residents, because they live in Potsdam. Right. Yes. There's relatively few Canadians working on that problem, except through the fisheries and aquatic ecology side.
Well, and I would say that's the same in Alaska, because before I moved there, you probably are familiar with that Selawik slump,
Mm-hmm.
which was a huge slump, and it shut off the river and just about destroyed the fishery, which was a huge subsistence fishery. So, yeah.
The people who prompted the biggest project we have in Canada on this were the Fort McPherson Renewable Resource Council, because they noticed that several of their streams were no longer good for fishing. So they got on to Steve Coquelle, actually, and said, you need to do a project here on what's happening in the Peel Plateau. And that really started everything off. But the effects are actually slightly greater further north than the Peel Plateau. So the areas where the rivers now are, I would say, are unrecognizable in comparison with what we would look at 5 years ago. That's slightly further north, and that would be in the Inuvik settlement region. Yeah. Dan.
So with limited resources for mitigation, for whatever else, what, at least in the Western Arctic, what would you say is the biggest concern from a landscape perspective?
Concern? Well, are you asking a political question or a scientific question? Political question. I'd say a political question, the biggest concern is the sumps. There's 170 contaminated sites, and they're not the responsibility of the people whose land they're on. They're the responsibility of somebody else. And they're a big, but now we have to also recognize that to clean them up is going to cost an awful lot. I think that's the biggest single issue that people are concerned about. In the long term, I suspect I mean the long term, but I mean the next 200 years, I suspect it's fisheries habitat that's going to be the most, people are going to be most concerned about. There is some concern about the stability of highways in the region, because most of the Inuvik Tuck Highway is built on icy ground, and much of the Dempster Highway is built on icy ground. But the highways have, very specific budgets, and they've got a lot of careful monitoring going on. So when they lose them, they have to reconstruct them within a week in order for people to get, driving up and down those things again. So highways would be the third area where I think, but I don't think the highways side of things is one that people are not aware of. I think people are very much aware of that. Fisheries, people are becoming aware of, and sumps, there's relatively few people aware, not locally, but in general, relatively few people aware of it.
Yeah, I would bet very few people know about it
Yeah.
outside of the permafrost, which is a huge expense. It makes me think of actually the oil wells in Alberta we're all going to have to pay to clean up.
Yeah.
Which, yeah.
I mean, it's exactly the same problem. But the difficult, in this particular case, you can only point the finger in one direction. That is that many of the sumps have been transferred back to the federal government, right? Because they got their clearance and everything. They were constructed in the 60s. By the 1980s, they were handed over. But it was the thinking at the time didn't include anything about climate change and containment.
Does make me wonder what's in the Russian Arctic.
Mm-hmm. Yeah.
There's still sumps that are still controlled by the oil companies?
Yes, because there was drilling associated with the potential for the Mackenzie gas project. So that's in 2004, and there are some of those are still oil company sumps. And the other thing, of course, is that devolution occurred in 2013, I think, or 2014, and so the territorial government is saying, "Oh, it's nothing to do with us." Right? All of those are grandfathered to federal. Yeah.
Sorry, I really like this. I don't know a whole lot about permafrost, but I found this really fascinating. And so, just one question I have is are we at the point now where this is irreversible? With the constant temperature constantly decreasing with all these slopes and all of the trenches and stuff. I was just wondering if we're at a point where it can't be reversed anymore.
Well, it depends what you mean by reversed.
Slowed down anymore.
Well, you can always slow things down, and you can slow things down. One way you can slow things down is by just clearing all the snow from everywhere. I was once talking to some international affairs students at Carleton, and they said, "Well, how are we going to protect our airstrips?" And I said, "Well, for a while you're going to build a bigger gravel pad." And then one of them, quite seriously, suggested we cover the whole of northern Canada with a gravel pad. And, it's just, so then you wonder, I mean, not only do you wonder about that person, but there you go. International studies students, mostly from other universities, perhaps even from Western Canada. But if someone thinks that is a viable mitigation, then we clearly have a problem with people understanding the environment that they're living in, So we can have specific mitigation for specific areas. So the answer to your question really is, if there's something that we really want to protect, we can do things about that. and we might be able to slow things down. For example, if we have a building that we really want to protect, we can try and cool the foundation down. And we can cool the foundation down either by having a heat pump, which is either a natural heat pump, like where we take heat out of it in the winter, extra heat out in the winter, or we can run a generator and extract heat, right? There's different ways of doing that, but that's for very specific things. And that's why I mentioned that there are engineering approaches that can be used in specific things, but you can't do it at the scale of the landscape. And so that means we have to think about the landscape as a dynamic environment. And what science will never tell you is what you should do, right? It'll tell you what are the results of what you do, or it'll tell you what happened, but it'll never tell you what you ought to do. That's a political question. That's why I asked the question to Dan. Is that a political question or a scientific question? And so that depends on what it is we want to do. And that's what management is. Environmental management is all about managing human activity to get our desired result.
So we kind of have to like pick and choose what we want to preserve and stuff up there?
Well, it's, it's thousands of square kilometers. And in the Western Arctic, there are 5,000 people total, right? So we're going to have to make that kind of decision. Yeah.
Thank you. This has been very thought-provoking. I guess I was wondering two things. The one is the microbial activity associated with permafrost.
Mm.
Are you concerned about that at all? And then the second part is from a bigger picture. In Calgary, we live here next to oil and gas country, and the biggest pocket of climate change deniers in the country. How do we get this message across? How do you convince people when they're so negative?
Well, can I answer the question first, and then I may have to ask you to repeat the first question, because usually that when someone says, "Can I answer you the second question first?" it's because they don't want to answer the first question, and they're trying to distract you. But the second question first. So 30 years ago, so that's the late 80s, the early 90s. Climate change was not a popular topic in the Western Arctic. A lot of people basically took the line, we've seen this all before. So when there was an event that took place, oh yes, I can remember something like this 30 years ago. Right? There were things that were happening which I interpreted, oh well, this is associated with climate change, like the beginning of that increase in the thawing of the ground. But they'd say, yes, but there was this one event that took place, and that one event is equivalent to what we're seeing. And in 1998, when we had that very, very warm year, there was a significant El Nino event. And so in an area where we don't, in Inuvik, usually there's snow at the end of May, lying around. In the middle of April, there was no snow, gone. And the people, the person who ran the Inuvik Research Center went out and bought an air conditioner for their building because it was now the middle of April and it was above zero. Right? What are we going to do? We need an air conditioner. So in other words, you could think of things like that. Now in the Western Arctic now, you will never hear anybody talk about that, because there have been so many events. In particular, the completion of the Inuvik-Tuktoyaktuk Highway was held up, the contractor said, because of climate change. What had happened was that it was meant to be finished in 2017, ready for all weather use, but in August, September, and early October 2017, you saw the effect of the landslides that year. It was very, very, very wet. And when you're building a road, you don't want lots of rain, because the surface of the embankment is just a mud pit. So you can't work on that. So they didn't work on it, and so the road wasn't finished. So then they handed in a bill to the government and said, now here's our bill for finishing the road. And they said, you haven't finished the road. We're not paying you. You can't not pay us. We've been working on this for 3 years. There's a lot of squawk over that. But the application was climate change, which we didn't foresee, has stopped us doing this. So now, and last week I was at a meeting in Inuvik of environmental monitors where I spoke quite a lot about some of the things that the temperatures change, none of them had any problem with any of that. In fact, what they were happy about was to know that scientists were putting numbers to what they had been observing, right? Because for some reason they think that numbers are more powerful than their observations. There's a reason for that which goes back to Socrates and Plato, but I won't bore you with that now. But what was your first question?
So I'm gonna go to the question, so. That's the nature of me, sorry.
Yes, yes.
It's just that if it took the people that are living in the midst of the biggest change that we're seeing on our planet right now, 30 years,
Mm-hmm.
to accept this, and these are not scientists, right?
No, these are ordinary people.
Ordinary people living on the land.
Yeah.
But in tune with the land.
Mm-hmm.
What's it gonna take for people around here? Because the change we see, we know this is happening out there,
Mm-hmm.
but the people around us are not accepting it. And I'm not in this room.
Yeah.
and people out in the streets.
So then the question is, if you look at what's happening in southwestern Australia, right, and then you imagine that that is never ever going to happen in British Columbia and Alberta, right, on that scale, you can carry on. But if what you see in Australia makes you think, oh, maybe there's something to this, then people might respond. But I'll just tell you one other thing. On Christmas evening, I was out, my wife and I went to supper with the people who live 2 doors away from us. And he used to work for Foreign Affairs. His name is Paul Willox. He did a PhD at Uppsala University. And his PhD at that time was on social democracy in Europe. And he had, during his PhD, he had the fortune to go to a conference in Madrid where all the social democrats from all over Europe were gathering, and the leaders of all the social democratic parties, and he had an opportunity for half an hour to meet each of these leaders. So there was about 15 of these people he spoke to. And so he spoke to Willy Brandt, and he spoke to some of the great names of the 1970s European political scene. One of them was a guy called González, who will not surprise you, was a Spaniard. And he ultimately became the Prime Minister of Spain when the Social Democrats were elected in the late 70s. But he was sitting down with González at the time that González was leader of the opposition in Spain. And he said to him, at what point do you think people in Europe need to think about what happened in the 1930s? In other words, he was asking him, will we see again the rise of fascism, essentially, but also looking at what happened in Russia in 1917. Yeah? So he's thinking in that framework. González says this. He says, when people have no threat to their security, if they're asked to choose between actions that improve security or actions that impair their freedom, in other words, liberalism, they will choose liberalism. But if their security is threatened, they will always choose security. Always. In other words, if your security is threatened, the government can do all kinds of things that abolish all sorts of liberties, right, and get away with it. But until that happens, you can't get away with putting constraints on people's liberty. Now, I quoted from a section from one of T.S. Eliot's talks. In another one that I've read, which is actually written in 1939, it's in a book, again, one of these little slim things. The title of the book is The Idea of a Christian Society. And he's not talking about a society where everyone goes to church. He's talking about a society that follows on from the 2,000 years of the European project. Right? So he's really talking about liberal democracy. And he's contrasting, in 1939, he's contrasting liberal democracy with what's going on in Germany under Hitler and what's going on in Russia under Stalin. So he's looking at those three things. And he says the thing about liberal democracy is that it always moves towards freedom of the individual. He refers to that as a negative influence on society. See, Margaret Thatcher said there's no such thing as society. She said the individual is the unit. Pierre Trudeau did exactly the same thing when he objected to Quebec having French language laws, right? Because the freedom of the individual trumps the benefit to society. Now, what Gonzalez says is, when your security is threatened, you may be willing to sacrifice your freedoms. We haven't got there yet, right? So we will fly around the world, right? We will drive big trucks. We will do all kinds of stuff. We'll build more buildings and use lots of concrete, right? We'll do all sorts of stuff because for us, our security is not threatened. That's why I think the flames in Australia are actually quite useful, because it threatens security. But we haven't had a disaster like that there's a little bit in the Okanagan, but in general, not nationally.
Sorry, the other quick question now, I think. At the very beginning was, are you not concerned about microbes being released as permafrost is melting?
Well, the other big issue of permafrost, apart from the security of infrastructure, is how much thawing of the organic material that I referred to in Brian's question. How much of the organic material that is buried at the top of permafrost and is currently frozen and hence inert, how much of that actually contains carbon that can be released? Some of it has been buried relatively rapidly, and that means the carbon hasn't been broken down. If the microbes work on that, either CO2 or methane will come out.
So I was thinking about from the fact that much of this has been frozen for 10,000 years, and the diseases, the microbes that are the source of some of these diseases from millennia ago, we may not have immunity to.
Yeah, but there's going to be all kinds of stuff that I don't have immunity to, but because I don't live in Mexico, and that's going to come up. So I'm not worried about it, because there's lots of things that I have to be worried about, and it's on that scale. I don't think that is as of high a concern. I don't think I could suggest to people that was a reason for wanting to deal with this problem in comparison with a number of other issues. So I'm not trying to deny your position. I'm just saying I don't believe it is as important as a bunch of other. And I'm sorry, I've gone on too long, as I can tell.
No, I was just saying it's a reason to stop doing archaeology in the permafrost.
Oh yes. Yeah. There's one more. Sorry.
I was just wondering, actually, as an international affairs student myself.
Oh yes, good. In gravel? In gravel? Do you study gravel? Gravel resources?
I was just wondering if there's any localized solutions for this, or is it just we need to take care of climate change?
Well, there's two issues. The first is adaptation, right? Because nobody can. Even if climate change stopped now, we're 3 degrees away from where we were 50 years ago, right? So the environment has changed, and as I said, many of the effects will occur gradually. So some of them are not yet in equilibrium with the current climate. So we're not in equilibrium now. If we're to re-establish an equilibrium, if we stop now, that'll take a long time. So there's lots of stuff that we've started that it doesn't matter what we do is going to happen, because the Earth system operates on a slower or on a longer time scale than the atmospheric system, because the atmosphere changes quickly. Like on Saturday or Sunday, you're going to be walking around here with no coat on. That's a pretty rapid change, 2 to 48 hours. That won't happen in the ground. So that's one thing. But the second thing is, so locally there has to be adaptation. Right? But we've started this wheel, right? And as I say, there are things that will occur whether we stop everything now or not. So then you have to think, how far do I actually want to go? And if you're in an environment where there are relatively few people, you don't have very much political muscle. Right? So it's very difficult for the people of the Western Arctic to influence the policy in Ottawa, which imagine then trying to influence the policy in the United Nations. Imagine trying to influence policy, worldwide. It's really difficult. And as I tried to indicate, I don't think we've reached the point yet where there is actually, in the Western democracies, there is a conviction that we need to start compelling people to adjust their way of life. We haven't done that. We haven't reached the stage of compulsion. We've reached the stage of attraction, right? We will give people tax breaks to put solar cells on their roofs, right? We might put taxation on gasoline. We may do that. Aviation gasoline is not taxed. We haven't yet seen taxation go on aircraft. And if you think of how much fuel an aircraft burns traveling between Ottawa and here, imagine what the price of the ticket would change if you said that for every kilogram there was going to be $1 tax. Right? Price would go up, and then people would be howling. And they say, you're taking away our ability to do this, that, and the other. And then we're at the root of the problem that she was describing.
So you don't think there's a localized solution?
Well, there are localized, there are local things that you can do to adapt, but there's no local solution to a global scale problem, if you see what I mean. That it's going to take global action, and there will be many local things that inspire global action, but we haven't yet got any way of making global compulsion. That just doesn't happen. The closest that happens is when, we have something like 1939. And then people are told, you can't do this and you can't do that, globally.